Hello everyone, and welcome to this lecture 45th for the course wastewater treatment and recycling. As this week we have been discussing about the tertiary or advanced treatment options, this particular class we will be talking about adsorption and ion exchange methods for the contaminants removal from wastewater at tertiary stage. Earlier we discussed the nutrient removal. So, in the adsorption and ion exchange system, they both essentially kind of try to trap the dissolved impurities in the aqueous phase, from the aqueous phase onto a surface, onto a solid surface in adsorption, and through an ionic interaction they kind of swap the ions in an ion exchange system. So, we will be talking about these two processes which are used as a tertiary scale treatment for many of the industrial applications, very rare in the municipal sewage treatment plant, because their tertiary treatment is usually not provided, and even if it is provided, processes like adsorption and ion exchange are not that frequently used. Only nutrient removal and some chemical precipitation methods can be used, but in industries these processes are pretty common, particularly the adsorption process, and ion exchange if one want to go for reuse or those kind of system. So, it is a method for demineralization as well, ion exchange. So, for people go for ion exchange before for treating waters, not only wastewater, in fact the raw water sources like say groundwater, if it is having high TDS or those kind of thing. So, it is treated with the ion exchange system for the removal of dissolved ions, so that the water can subsequently be used for the industrial applications or industrial purpose like in boiler or those kind of places. These are ion exchange is particularly used for softening the water. Okay, so removal of the hardness, which is essentially due to the ions of calcium and magnesium. So, the ion exchanger like geolite or those kind of thing can be used for water softening as well. We will discuss these in the prospect of tertiary treatment of the wastewater. So, to begin with, the adsorption in the wastewater treatment is typically used for removing the wide range of compounds from industrial wastewater, especially the kind of various micropollutants, non-degradable organic compounds, which we also call refractory organic compounds, and few metal from wastewater or source water. If it is not wastewater, as we said that it can be used for water treatment as well. So, it is used for those purpose as well. It is simply a mass transfer approach where the particles get accumulate onto a solid surface and thereby leave the water phase. So, that is essentially what happens. So, we have various micropollutants. Okay. Now, when we add an adsorbent to this water, what happens that the various these particles come and interact onto the surface of these adsorbents, and when we kind of make that water pass through, so these items retain on the surface of adsorbent, and the concentration of these contaminants in water reduces in the water which passes through the adsorbent media. So, adsorption actually is a word where there is retention takes place on the surface. We have a similar word absorption, where the particle in the water phase can actually come within the body of the adsorbent. Okay. So, then we call it absorption, and if something which is adsorbed gets back into the water phase, we call that process as desorption. So, there is adsorption, means the particle coming on and attaching to the surface of the adsorbent is adsorption. When it is entering into the body of the media, it is called absorption, and desorption is the reverse of adsorption. So, something which has attached to a solid surface gets back into the water phase. So, adsorption is more so of a basically term which is not only used for water treatment, it is a in general chemistry or chemical engineering, it is a far more common. It is used for the kind of trapment of the gases onto the solid surface, or many times at the solid liquid or gas liquid interfaces also. Okay. So, it is just a particle moving from a fluid or one phase to another phase is what will be referred as that in general terms. So, if we see the mechanism of adsorption, how it happens that there is, let us say, contaminant molecules are there, they come interact on. So, first step is the mass transfer to the adsorbent surface, then it diffuse into the pore of adsorbents, particularly for a porous material, okay, and then it gets adsorbed onto the surface of these pores, various pores. So, these are the subsequent steps through which the contaminant concentration in the aqueous phase decreases a lot as the contaminant has contained within the adsorbent media. Okay. So, if there is a kind of say surface film, so these are your elements, they come into the surface, then the step 1 they move onto the layer, they diffuse actually to the surface of the exact adsorbent, then step 2 they kind of diffuse into the adsorbent, penetrate into the adsorbent, and then in step 3 they get adsorbed onto these surfaces. So, that is essentially what happens in the process of adsorption. Typically adsorption is governed by two different, may be governed by two different kind of forces. There is physical adsorption, which is primarily due to the van der Waals forces, and that is why we can call it van der Waals adsorption as well, or commonly known as physisorption. Okay. So, that is one type of adsorption, physisorption. Then there is a chemisorption or chemical adsorption, where chemical bonding takes place between the adsorbent and adsorbate. The usual adsorption processes are always exothermic mostly, because it is a spontaneous, usually adsorption is a spontaneous process. So, the Gibbs free energy is negative, change in the Gibbs free energy is negative and the process is spontaneous. Usually it is exothermic processes. The van der Waals forces are weaker, so the bonding is weak here, whereas chemical forces are stronger. So, in majority of the cases chemisorption is far more stronger as opposed to the physisorption. They release heat of the order of 0.1 calorie per mole, and while they release the heat at the of the order of 10 kilocalorie per moles, both are exothermic. Since van der Waals forces are physical forces, and if the kinetic energy of the particle increases, it will again leave back the surface. So, they are reversible, whereas chemical adsorption may or may not be reversible, but depends on the nature of the reaction that has taken place. So, chemical adsorption often it is irreversible, but could be reversible as well if the nature of the forces are such that it can be reversed. So, for the wastewater treatment, if we say, the activated carbon is by far the most popular adsorbent, okay, which is most commonly used in the wastewater treatment for the removal of, particularly for the removal of refractory organics or non-biodegradable or non-degradable organics. There has been other adsorbents which has also been used under specific conditions. So, natural or synthetic zeolites which can be used for softening or those kind of thing, okay, that can be used. Natural clay minerals are used for very polar organic and inorganic metals or ions adsorption. Silica gel is used, activated alumina is used for the adsorption of various elements like arsenic or those kind of thing are adsorbed onto the activated alumina. Okay. Salicylic acid can also be used. So, we can use variety of materials at the adsorbent, whichever has a capacity to basically adsorb the target contaminant can be used. However, it is the activated alumina which has by far the most uses because of its retention spectrum, because of its ability to attract more, because of its nature or pore spaces or effectively surface area. So, adsorption is a process where the contaminant removal is taking place on the surface. So, more the surface area or more the active surface area rather, you will have high chances of contaminant getting removed. So, the carbon based adsorbents, if we see, there are activated carbon or carbon black, carbon nanotube, there are graphenes, okay, and the activated carbon which is more popular, actually we have various different grades and types of activated carbon. There is PAC, which is powdered activated carbon of the particle size 1 to 150 micrometer. There is granular activated carbon, So, that is in a granular shape, so little larger than 0.5 to 4 millimeter. Okay. And there is kind of extruded activated carbon as well, which has a little higher, could have kind of 0.8 to 4 millimeter size. So, activated the powdered activated carbon and granular activated carbon are the one which are more commonly or more frequently used. Okay. And these will have basically very fine pores, so that way a lot of surface area, there are a lot many micropores through which the particle can diffuse in and get adsorbed. Okay. So, if we see the kind of activated carbon, so their typical activated carbon will have numerous pores, and that is why provide a very large surface area for the treatment of water. These are prepared to exhibit kind of very high degree of porosity, because so there is a lot of scope for retaining the contaminants, because if there are not pores, so where the contaminant will retain, where they will get adsorbed. So, that is why having a high porosity is a good thing, and it then allows good flow through the water, a good flow through this adsorbent media as well for the water. So, contaminant typically adhere to these carbon granules, okay, or become trapped in the small pores within the activated carbon, okay, and these are efficient to remove various organic metals, chlorine, fluorine, radon and various other micropollutants that way. Okay. But it is basically the microbial contaminants, some of the metals, nitrates and inorganic contaminants are not that nicely removed through this adsorption process. So, if we see the typical activated carbon filters, okay, so we have kind of a filter will look like this. We will basically, we have to make the water interact with the activated carbon. So, we will have a layer of activated carbon for that matter, okay, and then we can have all those support layers various way. Okay. The water will come from the top, will be distributed from these headers, it will pass through these layers and then will be collected the bottom and then will drain from there. Okay. So, typical commercial unit will look like something this. So, we have this is your carbon layer, okay. Then there are kind of granules, gravels, pebbles, those kind of thing. There is a strainer plate, there are strainers, then on the strainer plates there are various hand holes. So, and then there is inlet and outlet arrangement. So, essentially water is passed through these layers, then it is through strainers, it is collected and then can be kind of taken out from the treated water can then be taken out that way. The filter, typical activated carbon filter under operation will have flow from this way. The under backwash will usually have a reverse flow, though the backwashing can also be done with a similar flow direction as well. And if we want to sterilize or kind of stripping, so we can pass through stream in order to sterilize or removing the microbial growth or microbial contamination if it has occurred in this layer of in this kind of column or adsorbent. So, that also can be done. Okay. Backwash is a process because so as we were discussing, the kind of adsorption process is the contaminant gets adsorbed onto the surface. Now, if you are keep on passing the contaminant and it is getting adsorbed onto the surface, so there will be a time when kind of the capacity of the adsorbent to adsorb these contaminants will exhaust, and thereafter if you pass the fluid, if you pass the water through this, there will not be any adsorption. So, in that case either there is two options, either you change this media, adsorption media, put a new adsorption media, or the other option is you regenerate this adsorption media. So, how do we regenerate these kind of like the sites on which the contaminants are trapped? So, we make them the contaminant again get released back into the into some solvent which we use for regenerate. So, let us say like for backwashing purpose, backwashing is done for that, okay, or regeneration is done for that. So, we have a column where, let us say, this is our adsorption media where it is packed. So, normally we are having flow like this, okay. When your contaminants impurities get entrapped in this, and then the, let us say, head loss decreases, or the efficiency of effluent water is not turning good, because that indicates that the capacity of this has exhausted. So, in order to regenerate it, what is done, that we can pass a kind of acid solution or those kind of things in which these contaminants have higher affinity for those solvents. So, if we pass those solvents over here, then it makes the kind of, it loosens those particles which are attached to the adsorbents, okay, and then it makes this system fluffy, and from here onwards if you keep on passing, so those contaminants will come back into the again solvent phase and will can be taken out, and the adsorbent layer, original adsorbent layer, is up for reuse purpose again. So, that is what is backwashing or regenerating the adsorbent, okay. And we can do the cleaning through stripping or sterilization depending on the requirements. So, if we see the effectiveness of the activated carbon adsorption, so there has been lot of research conducted with the removal of various parameters, various contaminants on the activated carbon adsorption, okay. So, there are variety of reports that way, it is not possible to compile all, like for various your chlorinated compound, it is a very good, activated carbon is a very good adsorbent for chlorinated compound. So, for variety of these chlorinated compounds, you see that efficiencies are usually greater than say 98-99%, barring a very few. So, let us say for this it is 86, 83, 87, those kind of thing, but usually you see very high efficiency of the removal of these contaminants. For BTEX, which is benzene, toluene, xylene kind of compounds, so efficiency is reported from 80 to 99.9%, for polyaromatic hydrocarbon 98 to 99.8%, for AOX greater than 90%, it can remove COD, colorant, alcohol, xylenes, phenols can be reduced from 60 to 90%, ammonium nitrogen with maximum flow 40 milligram per liter can actually remove up to 99%. So, that way, like the adsorbent is very effective in removal of a wide variety of contaminants, okay. However, the various dissolved metals or those kind of things, it has very limited applicability. So, since the activated carbon or those kind of thing can remove variety of organics or various apolar or non-polar or a few polar, like depending on the choice of adsorbent, quite a few polar compounds can also be removed. It is the metals or dissolved ions which are not removed, usually not removed from the adsorption. So, they can be removed through an ion exchange system. Now, ion exchange is a process which is typically used for these dissolved ionic impurities, and particularly hardness, because hardness also is caused by these dissolved ionic impurities, dissolved calcium and magnesium ions. So, the contaminant ions in water is removed by exchange with another ion which should be non-objectionable or not non-toxic kind of thing, okay. So, its kind of swapping takes place. So, what eventually happens in an ion exchange system, we have a polymer backbone through which a functional group is there, and the original resin comes with some ion attached with this, which is not that toxic, okay. So, let us say you are having sodium attached here, okay, or you are having OH ion attached here, and the red thing is your contaminant which you are willing to remove, okay. So, it could be any those sort of things, okay. Let us say it is arsenic, it is chromium or those kind of thing, okay, or some organic contaminant that some organic ion that way, okay. So, this is the thing that you want to remove. Now, what will happen that when it gets in contact with this resin, which we typically call as resin, ion exchange resin. So, as soon as it gets the water gets in the contact with the resin, this functional group has a higher affinity for this ion rather than this ion. So, what it will do, it will attach with this ion and in the process it will release this ion back into the water, but this ion is a non contaminated ion or not contaminating ion. So, we do not have too much of problem with getting this ion released in the water to a until unless it is an excessively high concentration like sodium, few milligram per liters of sodium or few microgram per liters of sodium is definitely not a problem, but even few microgram per liters of chromium or arsenic may create severe health issues. So, that way these ions are released and this is get trapped. So, after the interaction you will see a condition turns like this from here to here. Okay. So, this is what is essentially the ion exchange process. Okay. Now, this is a physico chemical process, physical chemical interaction in which ions are swapped between a solution phase and a solid resin phase. Okay. The solid resin phase is typically a elastic 3 dimensional hydrocarbon network which contains large number of these ionizable groups of electrostatically bound to the resin. So, this is important that it should have this large number of groups, because that is what will guide about the capacity of the exchanger. So, a synthetic resin is relatively well defined with a known ion exchange capacity, okay, and then it exchanges ions which it holds electrostatically on the surface with the ions of similar charge in the dissolved water. So, since it is exchanging, it will lead whatever it is attached to that will go to the water, whatsoever contaminated ion present in the water of the similar charge will come to the resin. Okay. So, the target ion is that way removed and kind of like this ion is retained temporarily with the resin, okay, and then once we try to regenerate the resin, we will talk about how to regenerate that. So, once we try to regenerate that resin, it comes back into the solution, regenerant solution that way, and that way it is removed from the water phase. So, if we see the various ion exchange resins, there are strong acid cations, strong base cations, weak acid cations and weak base cations. Okay. So, these are the different groups for the ion exchange resin, and they have the different kind of functional attributes. So, if we see the strong acid cations, they remove nearly all cations, okay, and replace them with a simple hydrogen ion. So, we will have a kind of resin like this attached, maybe attached with the hydrogen, and they can remove all these cations. Okay. So, that way your resin will now be attached with this and hydrogen could be released. We have weak acid cations which kind of associated with the alkalinity and those carbonic acids, those kind of thing which produce alkalinity that way. So, here your ion will be swapped with the alkalinity or those kind of ions which produce hardness or like temporary hardness kind of thing, which is due to the calcium, magnesium or with the carbonate or bicarbonates, and could remove the sodium also as well, but that is not a primary target though here. The strong base anions will similarly remove all encountered anions. So, whatsoever anions are coming in the system will usually be replaced with the OH ions, and then weak base anions, whereas like they will remove sulfuric, nitric and those hydrochloric acids kind of thing. Okay. So, that way these different types of resin have their different functional attributes. The resin comes with a specified properties. Okay. So, like your cation exchangers, there are inorganic like natural zeolite green sand has a capacity of this much, then there is another synthetic will have capacity of this much, there are organic exchanger, there are anion exchanger. So, they will come with a specified capacity, and a typical kind of resin, particularly the granulated resin, will look like this, what is there on the screen now. So, that is how the resins look like. These resins, the ion exchange is a process which works on a principle of selectivity. Okay. So, generally we will not have just one single ion in the water, particularly in the wastewater. So, wastewater will have a variety of ions, and the different ions do have the different potential to interact with the functional group of the ion exchange resins. So, some will be strongly bound, some will be less strongly bound. The one which kind of bonds more strongly will be selected beforehand by the resin, okay, by the functional group of the resin. So, those like more selective ions will bind first, okay, and then it will go to the less selective ions, or the ions which bond with the which have lesser strength for binding with those functional group. So, if resin comes with a weakly bound ion, okay, that will be preferably displaced by the stronger ions there. Even if in the water system, let us say we have a ion exchanger resin which is in the process of removal something, it has bind with one contaminant, but if in the water it comes in the vicinity of other contaminants which can actually bind more strongly. So, it will release even that contaminant and bind with the other. So, it all depends on the like how is the selectivity. So, this effect of selectivity can be used to kind of remove the distinct ions from the water and to replace them with the other. So, there is a preferential zone like who binds first with what's like typically a copper will bind before Hg, will bind before lead, will bind before nickel, will bind before zinc. So, that way we can have a series of selectivity or preferences who will bind first with the resins present in there. The ion exchange typical processes if we see, so there are anionic demineralizers or anionic ion exchange resins, cation demineralizers, okay, which contains cation resins, and there are mixed bed demineralizers which contains both anion and cation resins, okay. And depending on kind of type of the mineral in the effluent, we can select what kind of exchanger we need, okay. Cation exchanger with sodium, cation exchanger with hydrogen, cation exchanger with hydrogen, or an ion exchanger with chlorine, an ion exchanger with these things, and that way we can basically kind of select and eventually what minerals it converts to. If we see the typical process of the ion exchanger, so again it is done in a pressurized system. Ion exchange is a pretty fast, so we do not need much residence time, okay. It is a kind of instantaneous process as the ion, it is a chemical bond. So, as ion comes into the like vicinity of a contaminant with which it can bind more effectively, the resin will release that ion and bind with the other. So, it is just a matter of contact, and we do not need a large contact period for that. So, we can achieve that in a like pressurized conditions with quite rapid flow, okay. So, what typically happens that there will be resin here, the influent will be passed from the up, it will be distributed through the resin, and through an under drainage system it will be collected and it will be passed through, okay. So, that is what is the basic process, and in and around we can basically put in all other different mechanisms to deal with that. The ion exchangers needs to be reactivated or regenerated, the resin needs to be regenerated, and regeneration is essentially the process of activation of the resin again, reactivation of the resin again, which is carried out using a strong acid for the cation as a source of hydronium ions, and a caustic solution like sodium hydroxide as a source of hydroxyl ion for the anions. This regeneration of the exchange material involves like three different steps. So, first thing is backwashing, where kind of the normal flow is reversed. So, reversal of the normal flow to wash out any suspended material which is there in the bed and make that bed fluff. So, kind of like ease or lose out the bed that way, and then we introduce the regeneration chemical, which like as we said, that could be like for cation resin it could be strong acid, or for caustic solution for a kind of if you want to regenerate it for the anions, okay. So, that way then what is like this regenerated solution is passed to reactivate the resin by replacing the contaminant ion with the regenerant ion as we were targeting, and then it is rinsed. So, finally washing out the traces of the regenerant chemical if there is any, and then it is again up for the reuse. So, units are usually installed in duplicate to permit the continuous service during operation, because otherwise if you have stopped the unit for regeneration during that period, you may see no flow or that kind of thing, or if some unit fails, so how to basically deal with that. So, that is to be seen. This process of regeneration and process of normal service run or normal flow can be in the same direction or can be in the reverse direction. Okay. So, it is always prefer to have such process in the reverse direction, so which is called counter current kind of system or reverse flow regeneration. In the co-flow regeneration, what happens that this is say direction of my flow. So, these are the exhausted ions, so which are there in the water. So, initially as it will be getting entrapped from the top and slowly it will cover over there, but so almost things are covered. When we try to regenerate this, so what happens that again it will start losing from the bottom. Okay. Like here we are kind of putting the fresh solution here. So, initially release of the ions will be from here and it will keep on going down. So, your entire resin that will be covered, and by the time you regenerate you will be having like this. So, there might be a little this thing left in the bottom that way, and when you start again, when you basically recycle this back, so what you see trapment starts from this, but since there are some contaminant or some ions are there present in the bottom, so there might be a possibility of ion leakage, and that is why this kind of co-flow systems are not that preferred, whereas reverse flow are more preferred, where we are exhausting it from the top and then we are regenerating it from the bottom. So, there is no chance of accumulating anything in the bottom, because regeneration is from this side only. So, there is no kind of possibility of ion leakage. Okay. It can be in the other direction if we are having a upflow kind of system. So, we are flowing from the top, but then we have to regenerate from the bottom. So, either way it is good. This is more energy preferable, because then water flows in the downward direction. So, the gravity can also be utilized. Upflow will always have more energy exhaustive systems. So, that way this regeneration, the reverse flow regeneration is preferred as opposed to the co-flow regeneration, and these are that way called co-current and counter current kind of system. So, co-current system, when you are having feed water and regenerate in the same direction. In the counter current system, when we are having feed water from one direction and acid regenerant in the other direction. So, that way we can kind of set up, and as we were just discussing, that counter current systems are preferred over co-current systems. So, there are few limitations of the ion exchange systems. There are few with the your adsorption system as well. So, the capacity of the ion exchanger can get exhaust, and then we, or similarly for the adsorbent, can get exhaust, and then we have to kind of regenerate them. Now, this regeneration can take place to several cycles, but like it cannot work for infinite time period. So, after several cycles of regeneration, after kind of each cycle of regeneration, the capacity of the ion exchanger or capacity of the adsorbent decreases a little, and when the capacity goes below threshold, we have to discard that. So, that is one issue. Then ion exchangers particularly work in a differential pressures, okay, under pressurized systems. The adsorption processes can also be under pressurized system or can actually be under gravity flow system as well. Then there is issues of temperature. Okay. So, if the temperature are high, these process will not be suitable, because they will have higher solubility, higher kinetic energy into the system, and this binding and attaching to the functional group, or for that matter adsorption as well. So, if your molecules have higher kinetic energy, so they will not get easily adsorbed onto the surface. So, it is better done at lower temperature, and the higher temperature are not good for ion exchange or adsorption processes. Then there is a possibility of radiation exposure if we are dealing with those kind of thing, and the one of the major problem is in the form of competitive ions, because as we said that water matrix may have variety of ions, and it is not always like the, if we are targeting with some contaminant ion, and what if the adsorption is preferring adsorption, or for that matter ion exchange is preferring some other ion which is non-target ion. So, if those kind of ions are present with non-target ions which are having higher affinity, so that becomes a problem. Okay, they compete with the target ion, and then removal of the target ion or removal of the target contaminants will decrease that way. So, these are the systems which are typically used as a tertiary treatment for industrial wastewater, as we discussed in the beginning of this class. Okay. So, we will conclude the discussions here for this class, and in the next class we will talk about the another type of tertiary treatment or advanced treatment systems. We will discuss membrane processes and how they are used for the removal of various contaminants from the wastewater. Thank you.